Hello and welcome everyone to the VTC Spring in 2022. My name is Markus Hofbauer. I'm from the Chair of Media Technology at the Technical University of Munich. And today I will present you our work on traffic-aware multi-view video stream adaptation for teleoperated driving. Let me start with a quick motivation for this topic. In teleoperated driving, a human operator controls a vehicle from a remote environment. This can be a possible fallback mode for system failures of autonomous vehicles. The human operator perceives the remote environment via video streams of multiple camera views and then returns back or sends back the control commands to the vehicle. In mobile networks, the transmission rate of the network is often limited and changing over time. To avoid overshooting the network, we need a certain adaptation of these multiple video streams to fit the available transmission rate of the network. Since not all camera views are of same importance for the human operator in any situation, we propose an adaptation scheme that prioritizes certain camera views over others depending on the current traffic situation. In particular, in situations with a low transmission rate of the network, this prioritization scheme increases the quality on camera views most relevant for the human driver compared to a completely uniform distribution of the transmission rate over all camera views. Existing user studies investigated already the importance of video quality in teleoperated driving. For instance, a higher quality on the video stream improves the detection and perception of traffic signs or pedestrians. But which quality is even required at a minimum for every camera? Neumeier et al. Did this in a user study and figured out that at least 1 megabit per second should be available per camera view at a minimum. For the actual adaptation of the video streams, there are already existing works that try to improve the quality within a single camera view by compressing the most important objects within the camera view with a higher quality compared to the background, or using a joint rate control approach to achieve an equal quality distribution over all camera views. Since not all camera views are of the same importance in any situation, we propose to prioritize certain camera views over others depending on the current traffic situation. For the prioritization of the individual camera views, we consider two input information. First, the total available bitrate of the network and the status information of the vehicle. This status information includes the speed of the vehicle, the steering angle, and the gear position. Based on this vehicle status information, we estimate a priority score for every of the individual camera views. Multiplying this priority score with the total bitrate of the network, we get a certain bit budget for each of the individual camera views. And this is used as the target bitrate for the respective video encoder to compress the video stream. Then each of the individual video streams is transmitted over this mobile network to the client side, to the human operator, where the human perceives the remote situation through these video streams. For the actual prioritization, we use the following model, which assigns camera views that are in line with the current driving direction a higher priority. For instance, when steering to the left, the front and front left view will get a higher priority compared to the rear-facing camera views. In addition, we consider the actual vehicle speed. For instance, when going with a higher speed in straight direction, then the front camera view will get a higher priority compared to the side and rear-facing views. Using this model, we get a priority score and bit budget for every camera view. Next, we use a multidimensional adaptation scheme to estimate the optimal parameter combination for controlling the video encoder. These consist of the frame rate, the frame size, which is estimated for the given target bitrate. In addition, we apply a region of interest filter on the raw video input before it is fed into the encoder. This allows us for removing less important regions from the input frames. This filtered input video stream is then encoded using the optimal parameters estimated from the multidimensional adaptation model. The idea of the region of interest filtering is to remove less important content from the input frame before encoding. This increases the quality of the remaining areas when being encoded with the same bitrate. To include the most important regions for the driver, we update the region of interest mask based on the current driving direction. For instance, when steering to the right, this elliptical mask is shifted to the right. To further improve the resulting quality of the encoded video, we proposed a block-based mode for this filter mask, which is optimized for the video codec. To evaluate the proposed approach, we conducted several experiments in a user study. In total, we had 10 participants and evaluated on 3 driving scenarios. For the driving scenarios, we used a vehicle in simulation equipped with 6 cameras covering the surrounding of the vehicle. And we selected a total available transmission rate of the network with 6 megabits per second. In the first experiment, we evaluated the driving performance. For this, we compared the proposed prioritization scheme with a uniform distribution of the bitrate. This means instead of prioritizing certain camera views, we use the same bit budget for every of the individual camera views. To compare the driving performance, we measured the duration the participants used to complete the scenario. We measured the failure rate, this means having a lane invasion, a collision, or similar failures, and the red light rate. This means how many red lights did the participants miss. As you can see in the table, there are no really significant differences in the performance of the uniform mode compared to the prioritization mode. This can be explained that humans are still able to control the vehicle in an acceptable way, even if the quality is not as good as it could be. Since we could not observe significant differences in the actual driving performance, we evaluated the individual modules in separate experiments. As the first experiment to evaluate the view prioritization, the users had to rate the priority when observing the driving scenarios on a scale of 1 to 10, where low means the lowest priority for the certain driving scenario and 10 the highest. We did this for the same 3 driving scenarios, so turning left, turning right, and straight driving, and the results are shown in the table below. Next, we calculated the Spearman rank and Pearson correlation between these user ratings and the prioritization estimated by our model. The high scores of both metrics indicate a high correlation between our model and the user ratings, which suggests a good performance of the view prioritization model. To evaluate the performance of the region of interest masking, we encoded the video sequences of the 3 driving scenarios with and without the region of interest filter at the 4 quantization parameters 22, 27, 32 and 37. Then we compared the bitrate required for encoding and the resulting quality of the encoded video sequences for the baseline mode, which are the video sequences without any filtering, the continuous mode with a smooth elliptical mask, and the block-based mode. We plot the rate distortion curves of all 3 modes on the plot on the left, showing that the block-based mode achieves the best performance. This means it reaches the highest quality while at the same time requiring the fewest bitrate to compress the video. To evaluate these 3 curves in a single quality score, we calculated the so-called Bjontegaard Delta Rate, which is shown in the table on the right. The plot on the left corresponds to the second column on the table on the right, showing again that the block-based mode reaches the best performance. The final experiment evaluates the overall video quality using the prioritization mode compared to a uniform distribution. For this, we measure the PSNR and VMAF score for every camera view. Then we multiply this quality with the view priority rating from the user study to achieve an average quality score. The resulting average quality scores for the quality metric VMAF and the PSNR is shown in the table below. For both quality metrics, the proposed prioritization mode achieves about 5% higher quality compared to a uniform distribution. Now let me conclude this talk. We addressed the problem of limited transmission rate in mobile networks, which prevents the transmission of all camera views in full quality. To address this problem, we proposed a traffic-aware multi-view adaptation scheme to control the individual camera video streams. We consider the steering angle and the velocity of the vehicle to estimate a bit budget for every camera view. Then we use a multidimensional adaptation model to estimate the optimal frame rate, frame size and target bitrate for the video encoder. In addition, we applied region of interest filtering to remove less important regions from the input image before encoding. We performed several experiments to evaluate the proposed approach. While we could not see clear improvements in the driving performance, we achieved on average 5% higher video quality per camera view when considering the importance of the individual camera views on the current driving situation. For future work, we could not only consider the actual movement of the vehicle, but also object or region of interests available in the scene. Camera views that contain more objects within could be assigned a higher priority. With this, I want to conclude my talk. Thank you very much for your attention and feel free to contact us for any questions you might have. Besides, you can find the code available on GitHub on the link listed on this page.